this live. So we're testing our actually volumes here, our sounds and videos, but it's already on. So we're already live. So from your side, let me just check on your PowerPoint.
I can share my screen.
Okay. Okay. So
Can you see my screen?
yeah,
You can see my screen?
I'm not seeing your screen, Doc.
Uh,
Let me run your PowerPoint presentation here.
what about here? Can you see it here?
No, I'm just seeing you.
Okay, let's see.
Hello, good morning, Ma'am Iovi. May boses na po ba kami? Mayroon na. Good morning, Ma'am Shirley. Let me share. Oh, it's not there.
You can see me, but you cannot see my screen.
So, good morning. Okay, while waiting for the rest, let me check with the 18.
You cannot see my screen, Jonathan.
Let me check, sir. I'm not seeing here.
You're not seeing the screen.
Yeah.
So as long as you got the PowerPoint,
Thank you, Ma'am Shirley. We can hear you na po. Oh, that's great. Thank you for the feedback. We're just fixing something here from our guest. Our guest is from Maryland. So he'll be sharing his thoughts and expertise from the USA. So it's our first time to patch in and have someone from the other side of the globe, basically. Yeah. So practically. So let's just enjoy the day. It's a cool day, and I hope you're all doing good from the comforts of your homes. Ayan. So let me check on the PowerPoint. You're ready with the PowerPoint. Here is your presentation. Let me run it through. So if you right, wait, there you go. Okay.
okay, surely said me chicken
Yeah.
here.
All right. So let me show your Your topic for today. There.
All right, looks like
Okay. Okay, Doc. Are you able to see me from your side?
I don't see you, but I can see the presentation.
Presentation. Okay, let me just check on this one.
Okay.
Can you see the about that one?
Yeah, I see. All right. Are we ready? Jonathan, Jonathan, can anybody hear me? Can you hear me? Not not sure if you can see the PowerPoint very well. Um, I guess should I start? Hello? Okay, that's better. Okay, my talk today is about the applications of differential calculus, and I'm from Maryland. Just a brief introduction about myself. I graduated from University of Maryland, did my PhD there, and my master's is in Old Dominion University in Virginia, and Bachelor of Science is in the Philippines. That was like over 30 years ago. Uh, the, the outline, next slide, please, Jonathan. The, I'm going to be talking about what is differential calculus and why do we need to learn it. And we will go over some applications such as the maxima and minima and some applications for rates and how do we apply it to predict velocity and acceleration. Okay. Next slide, please. So, what is the differential calculus? What is it? Well, it's a branch of mathematics, basically. It deals with the derivative and the differential of a function. It could be a spatial function. It could be a trigonometric function, and this is discovered in the end of the 17th century by Newton and Leibniz. So in this case, as a nomenclature, an f of x is a function basically. You can look at it as a function that is a function of x. Like in this equation, the function of x squared plus 1. And if you let f of x equal to y, then this can be represented in two-dimensional relationships, like what I have here in this plot right here, where um, y is on the vertical line and the x-axis is the horizontal line. At x is equal to a, that's actually equal to 0. At x is equal to b, that's an arbitrary point. along this continuous function f of x. And what is a continuous function? Well, it's based on some assumptions here, and that if we know that this f of x is continuous, that means there's no discontinuity. It's a continuous, doesn't disconnect after x is equals to b, and such that if I will evaluate this equation for x is equal to a, it exists, and that also that's the same thing for if I will evaluate it for x is equal to b, this number exists. Okay, as well as if I take the limit as a function of x as x approaches a, it also exists, and that's also true for b. Okay, let's go to the next slide, which is another description about this function for a three dimension. In this case, this is a three-dimensional plane. Okay, and let's say a function of x and y. I will represent that as z, for example, and let's say it's the sum of x plus y. And let's say if y is equal to 1, x is equal to 3, then if I will evaluate this relationship, then I get z equals to 4. So this basically represents a point in the three-dimensional plane, such that x is equal to 3. So I have three units in here. Then I go to the y with 1 unit. Okay, then I project it to the z direction, so I get a point, which is point 3, comma 1, comma 4 brackets. Okay, that's basically what this relationship means as a function. So this is just one of the examples for a spatial function. Now, if I will insert t on this function, then it can be considered as a transient function. That means there's a time aspect of it, and it's one of those things that are very important and useful in mathematics, and also in any other field where we can apply mathematics. Okay, going to slide 5. This is I'm going to show you on slide 5, which is the next slide after this, is what are these differential derivatives? What are these? Oh, well, this simply pertains to the slope. Okay, in this case, uh, it's the difference in the differences of y2 and y1 points. Basically, y1 and y2 are points. X2 and x1 are points also along the x-axis. And basically, this is a definition of slope. And in fact, if x would represent time, this relationship here could be a rate problem. Okay, so this is how flexible it is. You can use time to replace x to make it in terms of time. Okay. Okay, going to the next slide. What is the limit? The definition of a limit on the next slide. Um, can you go to the next slide, Jonathan? Yes. This is the definition of a limit. It's it's a function of let's say it's f is a function such that x approaches the value a in this case, um, and then we can write this as the limit of the limit of f of x as x approaches a is equal to L. So this is represented by this drawing in here, the xy drawing. You can see that this x could be in between, the value of x could be in between a minus delta and a plus delta or sigma. I think that's the sigma. And then on the y-axis, you can see it could be in between this value L, it could be in between L minus epsilon or L plus epsilon. So, okay, so this basically is a point, it's a point in in this f of x line defined by this f of x line right here. Okay, go on to next point, next slide. Where does differentials and derivatives come from? In relationship with f of x, this is how it's defined. Okay, I showed this slide earlier from the previous slide, and it's basically a slope. Okay, and if you see the limit of f of x plus delta x, post parenthesis minus f of x, this actually represents delta y. Okay, the numerator is represents delta y, and the denominator is the delta x, which is the difference between x sub 2 and x sub 1. So this is basically if this x approaches zero, it's not necessarily exactly zero, but it's very close to zero. That's very, very small. It's called infinitesimal distance. It could be the distance could be at least 10,000 of a meter. Okay, one all over 10,000 of a meter. But it's not really. It doesn't represent atoms or molecules. It can represent a group of molecules, but it doesn't represent an atom or something like that. Because otherwise, if it's going to represent an atom, then you are in the quantum scale. But this one here is not on the quantum scale. We are on the continuum scale. Okay. So, but this is still very small, and we can use this to approximate phenomena. And we will go. We will try to go through that in the next few days. I will show you somehow how to do it. And this is a nomenclature how you write it. Okay, it's the derivative of the function of x over dx. Or you can say f prime x, that's the same thing. That's actually that prime right here means it's the first derivative. If there will be two of them, then there will be second derivative. Okay, in this case, it's a single derivative, and that is defined. That's also the same as dy over dx. Okay. Hopefully, there's no question on that. Feel free to shoot me a question on the chat. I should be able to see that. Okay, now heading to slide 8, which is the next one after this. Um, I will show you a little bit more about what is this slope and what is its relevance. Okay, it's actually this slope at the point of this f of x is actually the blue line, which represented here is actually a slope of that point, which is basically a tangent point. Okay, if this were if f of x is a function of y and t, all right, in this case, that point, the derivative of that dt with respect to time is essentially the velocity at that point. Okay, so that's how you use it in terms of looking at the relationship between space and time. Okay, in this case, the space is y and the time t is representing time. And the tangent line at the point p of that point, okay, is actually the slope or the velocity at that point. Okay, so that's what it is. That's how simple this is. It's not really complicated. Um, Although it looks like complicated, but it's actually just a slope. It's the point of tangency of that point. Okay. Let's go to why do we need to study differential calculus? That's actually the next one. The next slide. Um, why do we need to study it? Well, we a knowledge of this one provides us ability to find some of the, or maybe even predict some of the changing conditions that's happening in the system that is being investigated. Okay, let's say you had perform an experiment. In that experiment, you created X and Y plot. You have an input, which is X, and you have an output, which is Y, right? Okay, so let's say, so that basically means, you can, for every input that you put, like an X, you can determine what Y is. So let's say you're trying to trying to determine the number of COVID cases with respect to time, for example. Okay, before you are able to do some prediction, you need to have some data, and that data has to be reliable. If you don't have a reliable data, you don't have a model. As they say, garbage in, garbage out. So in this case, uh, even though we're using mathematics, for example, it's still very important and critical that we are recording the data accurately. Okay, so other interesting applications for differential calculus are organ transplants. You can use it for organ transplants, robotics, which I've used tremendously with robotics, electronic funds transfer. This is something to do with speed and rate, personal computers. You can use it for computational as a computational tool. You can derive some equations, then you can do some computational tools. Space flight is one good application. You can predict, if you know a relationship, if you're tracking a rocket going to the moon, for example, and you're tracking the space and time, you will be able to predict when it will reach the surface of the moon at any point of the moon. Because the moon is also spherical, near spherical, right? And Earth is also near spherical. So you can use trigonometric differential calculus to be able to predict those things. Okay, and basically everything that we touch today in our modern world is determined and predicted by differential calculus. The interesting thing part about this slide is that what I'm trying to show here is if we can determine something, we can predict something, we can control it. And that's the beauty about differential calculus. All right, let's look at some examples here. Okay, but before we go look at some, let me show you some concepts first, which is the first one is the maxima and minima. Next slide, please, Jonathan. Um, what is this maxima minima? If we can determine the slope and that slope is zero, it's actually a horizontal line represented by this dotted draw red line here. In this case, there are one, two, three, four points. There are 4 points in here that are zero slope. Okay, and there are two peaks and there are two minimums. We call it the minima, and that minima is called the saddle point. Okay, these are saddle points. If you look at the local maximum points, there are two of them. One of them is higher than the other. Okay, so if you have a function of x like this, you will have four values that represents a slope that is equals to zero. But by comparing the magnitude, you will be able to see which of this one will be um, maximum. And this is, this could be an experimental data also. Okay, so it could be experimental data as you track this relationship between X and Y. And hopefully everybody understood that part. Now, what about rates? Let's go to the rates. I will show you that in the next slide. This is a very good example that I saw from the internet this morning. I was looking at some application. This is an example here of a way of how you maximize something. Let's say a farmer bought a fence from from a hardware store, and this fence has a length of about 100 meters. Okay, and he wants to use this fence uh, to enclose an area adjacent to a wall, an existing wall, maybe his neighbor's wall. All right, because if he is a farmer, he wants to maximize the area so that he can plant. When he plants something on it, like maybe string beans or bagu beans or okra, for example, he can maximize his yield, right? So that's the application here. He can maximize his yield. So, so how do we do this? Well, to do this, we'll start with some knowledge about the perimeter and also some knowledge about the area, how you calculate that. P represents for the perimeter. That's basically the length of that fence. And if this is a block, it could be a rectangle, it could be square. We don't know. Let's assume it's a rectangle right now, such that x is not equal to y. Maybe y is longer, maybe x is shorter. We can assume that. But anyway, if that is, if those are the representation and they are at 90 degrees to each other, and these are rectangular block, this is a rectangular area, then I can write my perimeter as 2x plus y equals 100. And then if I will solve for y, I will transpose 2x to the other side, and I have 100 minus 2x, right? And then my area would be a equals x and y. That's a straightforward. For a lot of us who took geometry, that's your area, x times y. Okay, so if I will now substitute, I will use the same x, and I will express a in terms of single variable, in this case x only, and then I will make a as if it's y, then I will have 100 minus 2x. I will substitute that value of y into this equation in the area, and then I will have 100 minus 2x. Now, if I differentiate that now, if you go to the handwritten notes, right here, you can see that if I will differentiate it, I have 200 minus 8x. Okay. Okay. Those of you who have uh, taken some uh, uh, calculus, that should be the different derivative of a with respect to x. Okay, that's the slope going through that. So this is a quadratic equation. X squared, right? This is a quadratic equation. So if we differentiate that, it becomes a linear equation. Okay. Yes, okra plantation, and then 200 minus 8x, and then once you've done that, then we can set that to zero. A dA dx equals to zero. We set that to dA dx, then we will get the maximum area because the slope of of this relationship a as a function of x is it has a peak value. So if we set that to zero to get the slope of that peak value, then we get x is equal to 25 in this case. And therefore, solving for y, we get we get 50, and then solving for the maximum area, where then we have 1250 square meters. Very nice, right? This is a very practical example, and I like it as an example. Now, let's go to a rate of change, for example. This is really tough right here, the next one. It's about it's about a cube. Okay, this block of ice, let's say you bought it from let's say you are from Manila, you bought it from Baguio, and you notice that as you are traveling from Baguio to Manila to Baguio, you notice that there's a rate of change of each corner. It's changing at 1 millimeter per second. Now the question is, what is the rate? How what is the rate at which the volume is decreasing with respect to time when the edge is 5 centimeters long? Okay, so the cube is given the initial condition is that it's 10 centimeters long on each side, so it's like 1,000 cubic centimeters. But how fast is the volume changing when it melted and at certain time? We don't know what time that is. Okay. Well, the problem didn't specify what time that is, but it gives you it gives you the distance at 5 centimeters long. Okay, so here we are given that the dx over dt equals negative 1 meters per second, millimeters per second. And then the original one was 100 millimeters, right? Which is 10 times 10 centimeters. So that's I express them all in millimeters so that I don't get confused. Otherwise, we get confused and we will mixing oranges and apples here. So we want to make sure we are in the same unit, okay? So what is required is dVdt this way, that x equals to 50 millimeters. So the solution is okay. Well, we'll start with the volume of cube. The volume of cube is x cubed. Now, if I take a derivative of that with respect to x, using the derivative formula, 3x squared is the derivative of that. And then, because of this relationship, we will be able to do some chain rule. Why is it the chain rule? Where does the chain rule come from? Well, you have to think about it from the angle of our perspective, because the dVdt is in another perspective. It's not the same as it's what you call a Lagrangian Lagrangian perspective. It's another perspective, but the dx dt is in the local perspective. So that's why you have to use a chain rule here, and that chain rule will allow us to do some manipulation in here, as shown in this example here. Such that I know dvdx is already 3x squared. Then I make a chain rule such that I will multiply dx dt on it, and then I will cancel dx. It's almost like you're canceling dx here, delta x, and then you come up with dvdt. And then the dvdt now is now you can plug in your values now, which is dvdx, dv, I mean dv dx dt is equal to negative 1, right? Meters per second, and then the dvdx is 3x squared. So if I plug in all the values, then the rate of change of that volume with respect to time when x is equal to 50 millimeters is negative 7,500 cubic millimeter per second. That's what it is. Okay. All right. Hopefully that's this one is of course this is a simplified solution, but this is an example, a good example of how we use calculus in this manner. There's no other way how you can calculus solve this problem other than to use calculus. Okay. Now let's go to the next one here. Let's go to the next problem here. Okay, this is another problem here. This is about the derivation of the moment of inertia of a moving body about a radius that is r. R is given here. Okay. And but what is this moment of inertia? Well, the moment of inertia, a quantity that determines the torque needed for a desired angular acceleration about the rotational axis. So if I will draw this, if you see the figure on the left, this is actually like Goliath like King David trying to, twirl this slingshot, and he's spinning it at a certain velocity, rotational velocity, right? That body has a mass. It's given. It's given as m, and where King David was, he is at the y-axis. It's at the intersection with these 3 points. That's where his hand is, and he's rotating it like that. He's rotating it. If you look at it from the y-axis, he's rotating it counterclockwise. Okay. If you look at it from the y-axis, positive y-axis is counterclockwise. If you look at it from the negative y-axis, it's clockwise. Okay. So this is how you look at this one. This is 3 dimensions. So I'm given with my radius, I'm given with m, which is the mass of the body, then one requires the rotational moment of inertia. Since this is about the torque, we know that the torque is force times distance of the rotation. In this case, if F is represents force, R represents uh, the distance of rotation of that mass to the center of rotation, then it's R. But F is okay, is another term that we can calculate mass from the Newton's second law of motion. Okay, you in this case, it can be calculated with if you know the mass and then you also know the acceleration, then you can determine that force. And that acceleration is a derivative of velocity with respect to time. Okay, so v here is velocity. Now go to the next slide. Um, we go to the next slide. The velocity is the derivative of. We also know that the velocity is the derivative of the displacement, which is represented as s with respect to time. WRT means with respect to time. So the velocity in this case is ds dt, derivative of s with respect to time. But what is s? S is basically um, still in the previous slide. Still go back to the previous slide. Jonathan, let's see. Go back to slide 14. I think we are on slide 15. But anyway, if you now substitute that the values of dvdt, which is the second derivative of the angle, you'll be able to see it. Okay. So this case, that's the force and that's the torque. And basically the moment of inertia here is basically mass times the radius times the angular acceleration. In this case, mr alpha. That's the moment of inertia here. And then the torque can be calculated as mr squared alpha. And your moment of inertia will be that variable, the first two terms, which is mr squared. That's the moment of inertia. Okay, that's basically the end of my presentation. I hope you learned a little bit about it. Yeah, it's a combination of physics. That's one of the things I like about calculus because it touches all the subjects, especially physics, heat transfer, mechanics. Um, you can also touch economics. If you want to minimize the cost, for example, like what we saw in the fence problem with the farmer trying to maximize the area, that's actually an economics problem. So this is really, it has a lot of good practical applications. Okay. Um, that's all I have really about this subject matter. Tomorrow I will go over some topics on integral calculus. Integral calculus and differential calculus are intertwined. They go together. They go hand in hand. And if you go into the three dimensions, it becomes partial differential equations. If you are staying in the two dimensions, if you mix calculus, integral, and differential together, we call that differential equations. Okay, so that's a that those are mathematical formulations that are important even to this day. Especially with the advent of computers now, we want to develop computational tools for designing something. It could be a chemical process, a manufacturing process using 3D printing, or it could be trying to predict the effect of earthquakes. Continue some of this also. Okay.
Wow.
All
How
right.
about the big hand?
Ah,
Doc, okay lang po ba? Talagang masarap ang makinig at matuto.
oh yeah. Thank you.
Diretso, no? Diretso na tayo kaagad. So, thank you so much for the time
Yes.
and sharing of your expertise. Si Doc po ay talagang designer, researcher siya ng mga matitinding projects sa US and international. Right now, meron siyang company, so if you could share something more of that, how are you applying the your expertise in mathematics sa mga projects mo,
Yeah.
lalo na sa robotics.
Yeah, yeah. We have a project right now to develop a computational tool for. I can share you my. Maybe you can share my screen. Uh, let's see. Let's see if we can share my screen here. Is you around, Jonathan? Or you're cut off? I don't think. I don't. Are we still? Can I still see you guys? Are you still around?
You'll still have your session tomorrow. Perhaps you can share more
I can.
of it tomorrow. Yes.
Yeah, that's right.
And,
That's right.
and
I'll
may
share
meron silang
tomorrow.
aabangan.
Yeah, yeah, yeah. I'll share you the clip also
Sir
about.
Bricks Vlogs actually is requesting for statistics din daw po sana. So
Ah,
sana po we can extend more topics such like this on mathematics para sa ating mga
mhm, mhm,
participants. We
mhm.
are all facing brilliant teachers po ang ating mga participants. And they are much willing to learn with us. Maraming salamat din daw po. Oh.
Okay.
So we are reading some comments and we appreciate your comments and joining us in today's uh, session. You're welcome po. Nosebleed po tayo. Pare-pareho po tayong nosebleed. We're all learning together. Diretsong English. Pero si Doc is also from Cordillera like me. So you can speak to him in Ilocano, Tagalog, Filipino, whatever. Ano. So we
Yes.
really appreciate your time, Doc.
Thank
Thank you
you.
for joining us.
Thank you for
And
everyone.
Dr. Molintas is actually the chairman of our group, United Filipino American Foundations, and they're the ones actually hosting and sponsoring our certificates, and we appreciate that. Mhm. Thank you, Dao, from Ma'am Effie
Thank you. We'll,
Pontillas.
we'll touch you tomorrow for
Like this.
another round of exciting time. Thank you.
Mhm. Wala po ba daw code, sabi ni Ma'am Genia.
Code. Anong code yun?
Mhm. So marami nagpapasalamat, sabi ni Ma'am Eloise. Wow, thanks Sir Henry.
Welcome, welcome. Hope you
Mhm.
learned something.
Yeah. Thank you, sir. Take care and God bless.
God bless. Good night. Okay. Okay,
Thank
bye
you.
bye.
God bless you.
Right. Bye bye.
And good night. Have a sweet dreams.
Good dreams. Yeah. Good night.
God bless. God bless everyone. So we're now closing for today, and may we all stay safe. In the half of the A team, thank you all for joining today. So uh, please don't forget your evaluation. Perhaps one of us will be sharing that. We appreciate your presence today. Thank you. Uh, so abangan po yung evaluation form that will be sent online. Thank you. God bless you all.